Hello everyone and welcome back. In the last video, we looked through some visualization of embedding using embedding projector. At the same time, we used a pre-trained embedding layer into our model with the help of civil dataset. Next, we want to understand the meaning of the words and the sentences that we have. Also, we want to create more sentences by the use of recurrent neural network. Now, let's just dive into chapter 7, which is all about recurrent neural networks for NLP. In chapter 5, you saw how to tokenize and sequence text, turning sentences into tensors of numbers that could then be fed into neural network. You then extended that in chapter 6 by looking at embeddings, a way to have words with similar meanings clustered together to enable the calculation of sentiment. This worked really well. You saw how building a sarcasm classifier, but there's a limitation. Namely, that sentences aren't just bags of words. Often, the order in which the words appear will dictate their overall meaning. And that's true even. Imagine you have any sentence, say, the sky is blue, and according to what we have learned till chapter 6, if it's just a bag of words, it would be sky is blue. But imagine if we reverse the whole words, they don't make any meaning then. Like blue sky is. The sentence doesn't make any meaning, right? It has to be in the same sentence, in the same wordings, and has to be with adjectives that add meaning to the words. Adjectives can add to or change the meaning of the nouns they appear beside. For example, the word blue might be meaningless from a sentiment perspective, as might sky, but when you put them together, they to get blue sky, it's a clear sentiment that's usually positive. And some nouns may qualify others, such as rain, cloud, writing, desk, coffee, mug. To take sentences like this into account, an additional approach is needed, and that is to factor recurrence into the model architecture. In this chapter, you'll look at different ways of doing this. We'll explore how sequence information can be learned and how this information can be used to create a type of model that is better able to understand text, the RNN network. The basis of recurrence. So this book doesn't go directly too deep into recurrent neural network. It will just give you an overlay of it, just a brief and how RNN works. To understand how RNN recurrence might work, let's first consider the limitation of the models we have used so far. Ultimately, creating a model looks a bit like figure 7-1. Let's take you there. So, what we think of a model is that we feed in the data, we feed in the labels, and the model is trained upon them and it gives us the rules, right? You provide the data and labels and define a model architecture, and the model learns the rules that fit the data to the labels. Those rules then become available to you as an API, and that will give you back predicted labels for the future data. But as you can see, the data is lumped in wholesale. There is no granularity involved and no effort to understand the sequence in which that data occurs. This means that the word blue and sky have no different meaning in sentences such as today I am blue because the sky is gray, and today I am happy and there's a beautiful blue sky. To us, the difference is the use of these words is obvious, but to a model with architecture shown here, there is no difference. So as we can understood what we have read till now is that for us as a human being, we know the difference between the two sentences I've just read. The first one is today I am blue because the sky is grey, and the second one is today I am happy and there's a beautiful blue sky. But to a model that you are seeing on your screens, it does not know that these two sentences are different because it does not understand the meaning behind that. For it contains blue. Both the sentences contains the word blue and sky. So the model won't be able to give a correct comparison between the two. How to fix that? Let's first explore the nature of recurrence, and from there you will be able to see how basic RNN can work. Consider the famous Fibonacci series of numbers. In case you're not familiar, what this series is 1, 2, 3, 5, 8, 13, 21, 34, 55, and 89. What's happening here is the idea behind this is that the next or the preceding number is the sum of the behind two numbers. So means like 1 is as it is, 1 plus 2 gives 3, 3 plus 2 gives 5, 5 plus 3 gives 8, 8 plus 5 gives 13, and so on. So we can place this in a computational graph to get this. So you can see that 1 and 2 are added and gives 3, and the 2 is then carried forward again and is added to 3 again to give 5, and the 3 is then carried forward again. Similarly, 3 and 5 are added again to give 8, and 5 is also carried forward. Here you can see that we feed 1 and 2 into the function and get 3 as output. We carry the second parameter 2 over to the next step and feed it into the function along with the output of the previous step, that is 3. The output of this is 5 and it gets fed into the function with the second parameter from the previous step 3 to produce an output of 8. This process continues indefinitely with every operation depending on those before it. The one at the top left sort of survives through the process. It's an element of 3 that gets fed into second operation. It's an element of 5 that gets fed into the third, and so on. Thus, some of the essence of 1 is preserved throughout the sequence, though its impact on overall value is diminished. So what is the whole gist of this is that the 1 that was initially on the left top corner, it is somehow still preserved, and thus its value is diminishing, but it is still preserved as a very small part of the whole sequence. This is analogous to how recurrent neuron is architected. You can see the typical representation of a recurrent neuron. So this is a recurrent neuron where you feed an xt to a function that gives you yt, and the function feeds itself again. The value of x is fed into function f at a time step, so it's typically labeled xt. This produces an output y at that time step, which is typically labeled yt. It also produces a value that is fed forward to the next step, which is indicated by the arrow from f to itself. So the arrow that is depicted here that goes from f to f again is actually moved to the next function for the next step. This is made a little clear if you look at how recurrent neurons work beside each other across time steps, which you can see in the figure 7-5. Here is a full-fledged time-stepped recurrent neurons. So you can see first we feed in x naught, operated to get y naught, the value that is passed forward. The next step gets the value and x1 and produces y1 and the value that's passed forward. The next one gets the value x2 and produces y2 and pass forward value, and so on down the line. This is similar to what you saw in the Fibonacci series. That means that if we reach xn, then there will be some part of x naught, but it will be very small and diminishing in value, but it will be there, it won't get vanished. Next is extending recurrence for language. In the previous section, you saw how a recurrent neural network operating over several time steps can help maintain context across a sequence. Indeed, RNNs will be used for sequence modeling later in this book. But there is a nuance when it comes to language that can be mixed or missed when using a simple RNN like those in figure 4 and 5. As in Fibonacci series example mentioned earlier, the amount of text or context that's carried over will diminish over time. The effect of output on neuron at step 1 is huge at step 2, smaller at step 3, smaller still at step 4, and so on. So, if we have a sentence like, today has a beautiful blue something, the word blue will have a strong impact on the next word. We can guess that it's likely to be sky. But what about context that comes from further back in the sentence? For example, consider a sentence, I lived in Ireland, so in high school I had to learn how to speak and write something. That something is Gaelic, but the word that really gives us that context is Ireland, which is much further back in the sentence. Thus, for us to be able to recognize what something should be, a way for context to be preserved across a longer distance is needed. The short-term memory of RNN needs to get along, and in recognition of this, an enhancement in architecture called long short-term memory or LSTM was invented. So what's the logic behind all this is that if we have a long sentence and we want to find the answer at the right end of that sentence, which has some context with the first word of the sentence, then we need to make sure that we remember that first word, which will have some impact on the last answer that we have to write. While I won't go into detail on underlying architecture of how LSTMs work and high-level diagram shown in 7-6, this is the high-level view of LSTM architecture. It's all the same, just a cell state is added to RNN network. To learn more to the internal operations, you can check out an excellent blog by Christopher Ola on the subject. The LSTM architecture enhances the basic RNN by adding a cell state that enables context to be maintained not just from cell step to step, but across the entire sequence of steps. So, the cell state that we just heard about or just we had a look to is used to enable or that enables context to be maintained. So not just from step to step but across the entire sequence of steps. So the cell state is used to just keep the context maintained. Remembering that these are neurons learning in the way neurons do, you can see that this ensures that the context that is important will be learned over time. An important part of an LSTM is that it can be bidirectional. The time steps are iterated both forward and backward so that the context can be learned in both directions. So that's the best part of LSTM, that it is bidirectional. So the time steps can be iterated both forward and backward. So you can see in this diagram, the flow of information is actually bidirectional. In this way, evaluation in the direction from 0 to number of steps is done, as is evaluation from number of steps to 0. At each step, The Y result is an aggregation of forward pass and backward pass. So this is something important, that at every step the Y result you get is actually the aggregation of forward and backward pass. So you'll understand better from this figure here. So you can see that consider each neuron at each time step to be F0, F1 and F2, right? The direction of time step is shown. So the calculation at F1 in forward direction is F1 minus and forward, and in the reverse direction is backward minus F1, right? The values of these are aggregated to give value of Y at that time step. Additionally, the cell state is bidirectional. This can be really useful for managing context in sentences. Again, considering the sentence like I lived in Ireland, so in high school I had to learn how to speak and write something. You can see how the something can be qualified to be Gaelic by the context word Ireland. But what if it were the other way around? If it says I lived in this country, so in high school I had to learn how to speak and write Gaelic. You can see that by going backward through the sentence, we can learn about what this country should be. So here the context word is Gaelic. From that we'll understand that Gaelic is a language that is spoken in Ireland. So that word I lived in Ireland would be written there. Thus, using bidirectional LSTMs can be very powerful for understanding sentiment in text, as you'll see in chapter 8. They're very powerful for generating text too. Of course, there's a lot going on with LSTMs, in particular bidirectional ones. So, expect training to be slow. Here's what's it's worth investing into GPUs. So the training would be a bit fast, but you can easily use Google Colab's hosted GPUs for better results. Next, let's create a text classifier with Rnns. So we'll be just using our sarcasm dataset, and there will be like a few bit changes that we'll be doing. In chapter 6, we experimented with that. In that case, words were turned into vectors before being aggregated and then fed into dense layers for classification. When using an RNN layer such as an LSTM, you don't have to do any aggregation and can feed the output to embedding layer directly into recurrent layer. When it comes to dimensionality of recurrent layer, a thumb rule you will often see is that it's the same size as the embedding dimension. This isn't necessary but can be a good starting point. Note that while in chapter 6 I mentioned that embedding dimension is often the fourth root of the size of the vocabulary, when using RNNs you'll often see that that rule is ignored because it would make the size of the recurrent layer too small. So, for example, the simple model architecture for sarcasm classifier you developed in chapter 6 could be updated to this. So, there is no much of big changes there. We actually had the embedding layer with vocab size and embedding dimensions. Now we are just adding the layers, the bidirectional layer, the LSTM layer with the embedding dimension. So we are not adding anything in the parameters. We are reusing the parameters only, and also we don't have to do any aggregation, so that average layer that we won't be using anymore. So we don't need aggregation because the LSTM layer will take care of it, right? So the loss function and the classifier can be set to this. Note that the learning rate is 0.4 times 0 and 1, that is 1 to the power 10 of minus 5. Adam, that is the optimizer that we'll be using, is as it is, just we've changed the learning rate. Amsgrad is false. So, and model.compile is as it is. Nothing we have changed, just added a single bidirectional layer, LSTM layer. When you print out model architecture summary, you'll see something like this. Note that the vocab size is to 20,000 and the dimensions, the embedding dimensions is 64 that we have changed. Earlier we were using vocab size of 2,000. Now it's 20,000, while the embedding dimension was around 16. Now it's 64. This gives us around 1 to 8, 4 times 0 parameter in the embedding layer. And the bidirectional layer will have 128 neurons. So once this is done, we've printed the summary. We'll just compile and run it, fit the model. As you can see, the accuracy of the network on training data rapidly climbs above 90%, but the validation data plateaus around 80%. This is similar to figures we got earlier, but when we inspect the loss charts, shows that while the loss for validation set diverged after 15 epochs, it also flattened out to a much lower value than the loss chart for the previous one, despite using 20,000 words instead of 2,000. Right? So you can see the validation accuracy was increasing, but it's flattened out around approximate to be 80%, while the training accuracy has gone to 90%. And let's see the loss. Yeah, so loss is going down for validation, and the accuracy loss, training loss is going down, but the validation loss is approximately flattening out. This was just a single LSTM layer. However, in the next section, you will see stacked LSTMs and explore the impact of that stacked LSTMs on accuracy for classifying this data set. So for stacking LSTMs, in the last previous section, we saw that use of LSTMs after the embedding layer to help classifying the contents of the sarcasm dataset, but LSTMs can be stacked on top of each other as well. So how are we going to do that? Is that we already had this line, right? Layers.bidirectional, tf.keras.layers LSTM, and we just passed in the embedding that time. Now we're just passing it one more parameter, that is return sequences equals true, and this is the second LSTM layer. So we said we were stacking the LSTM layers, and here we are stacking them. It's pretty straightforward. You add them as extra layers just like you would with a dense layer, but with the exception that all the layers prior to the last one will need to have their return sequences property set true. Right? So let's see. The final layer can also have return sequences equals true set, in which case it will return sequences of values to dense layer for classification. So instead of single ones. This can be handy when passing the output of the model. We'll discuss that later. While we have added or stacked the LSTM layers, let's see what kind of model summary we get. So we see that both of the LSTMs have 128 neurons and kind of not much for parameters. While we can see this, let's see that adding extra layer can give us roughly 100,000 parameters that need to be learned, an increase of about 8%. So this will slow our network down, but the cost is relatively low if there is a reasonable benefit. So after training for 30 epochs, let's see the validation. The accuracy on validation set is flat. Examining the loss tells a different story. So this is the accuracy, and you can see it's about 80% only for validation and skyrocketing for training. And let's see what's happening for the loss. So we can see that this is overfitting. This is completely overfitting, that the validation loss was going down and down till 50, till 0.5, and then it skyrocketed again, and it's overfitting indicated by the training accuracy climbing towards 100% as the loss falls smoothly While the validation accuracy is relatively steady, the loss increases drastically. As a result, the model getting over specialized in the training set. So this shows that adding another layer of LSTM has worsened our the whole criteria, right? Optimizing stacked LSTM. So now if our model is overfitting, what we do is we try to optimize the losses. In chapter 6, we saw that a very effective method to reduce overfitting was reduce the learning rate, right? So now what are we going to do is we're going to reduce the learning rate by 20%. So we are just gonna use 0 point, that's 5 times of zeros and 8, right? And then we just train it and see what we get. Demonstrates that impact on the training. There doesn't seem to be much difference, though the curves, particularly for validation set, are a little smoother. So nothing much happens, just the curves become more smoother. While an initial look at 7-14 similarly suggests minimal impact on the loss due to reduced learning rate, it's worth looking a little closer. Despite the shape of the curve being roughly similar, the rate of loss increase is clearly lower. So after 30 epochs, it's around 0.6, whereas the higher learning rate, it was close to 0.8. So we can say that it's still on the verge of overfitting only. We can see the loss of validation is rocketing, but it's much smoother than the before one. So there is some bit change after we have changed or reduced our learning rate. So next thing we do for overfitting is using dropout layer. So let's just go and use it. In addition to changing the learning rate parameter, it's also worth considering using dropout in LSTM layers. It works exactly the same as for dense layers as discussed in chapter 3, where random neurons are dropped to prevent proximity bias from impacting the learning. So dropout layer is here. So we just add dropout equals 0.2, that is around 20% of dropping out on each. So do note that implementing dropout will greatly slow down your training. In my case, using Colab, it went from 10 seconds to per epoch to 180 seconds. So there is like really slowing down on the training side. But the accuracy is good. It looks quite good. And we can say that validation and training accuracy, it's kind of the same like the previous ones. I don't see much of the change there. And using dropout doesn't have much effect on the accuracy of the network, which is good. There's always a worry for that losing neurons will change the model accuracy, but it doesn't do that here, so it's a good sign. But let's see what's the effect on the loss side. So yes, you can see that the loss is coming down and flattening. While the curves are clearly diverging, they are closer than they were previously, and the validation set is flattening out at loss of about 0.5. That's greatly significant better than 0.8 seen previously. That as this example shows, dropout is another handy technique which can improve the performance of LSTM based Rnns. It's worth exploring these techniques to avoid overfitting in your data, as well as the techniques to pre-process your data that we covered in chapter 6. But there's one thing that we haven't tried, and a form of transfer learning where you can use pre-learned embeddings for words instead of trying to learn your own. We'll explore that next. So I'll be dropping off it here only, and we'll be continuing a pre-trained embedding session in the next video. And for now, I'll just jump to the Colab, and you can have a look at what are the results of all this training and overfitting and how we overcome the techniques and how we use the LSTM network. So we'll just go through that and we'll understand it better through code only. So let's jump to the Colab. So let's get started with that Colab. First, I'm just gonna change the runtime to GPU because I don't want it to take so much of time, right? So I've linked a collab here for reference for our next, that is pre-trained model, pre-trained embedding. So we'll just give a look at that in the next video, but let's get started with this. So while it's allocating, we'll just import TensorFlow datasets, beautiful soup, TensorFlow uh, tokenizer and pad sequences. Let's just keep moving, and this is the whole same code that we've already seen. There is nothing new in it, so I'll just be running it through. So we've imported strings, we have whole stop words here, so we're just getting the data here, just dividing, loading the JSON file, then getting the sentences, labels, and URLs, splitting them, removing the punctuations and all, right? So let's run and get the length of sentences is 26. So it's around 26K, and we'll be using 23 out of it. So let's just do this way. And right, so it's the sequences, just padding sequences, converting text into sequences. So we have done it here. That new has sequence as the number 2, Trump is allocated 3, man is allocated 4. Then we're just converting the sequences to a NumPy array, and the dimensions are 64 as we have already read. Here is a model. Then we have embedding layer, we have two LSTM layers, we have applied dropout here, we have returned sequence equals true, and let's just run this one. Okay, there is some error here saying that dropout equals 0.2. Let me just fix this. So let's just small d, and similarly here it is also small d. I hope it runs now. Right, small d, guys. Then we have Atom Optimizer, we have replaced with the learning rate, we have model.summary. So let's get a model.summary. You can see 128 neurons to both LSTM layers and 64 to the embedding layer. Then just hit model.fit, and this will take a lot of time. Even the GPU is running, it will still take some time. So let's just wait for it to run our first epoch. And meanwhile, you can just get this whole code on GitHub. The link would be in the description. So, and if you have any problems or doubts, do post it in the comments. So first epoch is here. We get the training accuracy of 55 and the validation for 57. So we can say validation is doing good, but we can't just say on basis of like 1 or 2 epochs. We have to look through all. So let's just wait and see what we get once this whole model is trained, and then we'll look into the graphs for loss and accuracy. So our training is done. You can see that as I've shown you earlier, there was some kind of good thing coming, that our training accuracy was around 56 while the validation accuracy was hitting 63. But after some time, I'll say on the 6th epoch, you can see that this just changed. The accuracy for training was 64.8 while the accuracy for validation was 64.79. And that was the point where the validation accuracy went down drastically and the accuracy for training went up drastically. So when we are all done, finally we can see the validation accuracy is 61.3 while the training accuracy is 91.2. That is a huge margin. And when we plot it, we can see that the accuracy and the for validation and training, there is a drastic difference, and there is a lot of jiggles in between as well, right? So there will be some kind of problem in this when we work with this kind of model, and we really need to fine tune it to lower down the overfitting. We can see there's a whole lot of overfitting in here. So I'll also try down to decrease this overfitting to my extent and using hit and trial methods. And at the same time, it's up to you as well to hit and try these methods, and let's see if we can hit the target of reducing the overfitting as much as we can, right? So thank you for visiting and looking into this video. Next time we'll be understanding some pre-trained embeddings that we can use for reducing overfitting, and how it's done, and hopefully we'll be able to just reduce this overfitting as well. So I'll see you next time. Thank you.